All that equipment is for carrying out organic synthesis on a large scale. The end product is acetaldehyde, and the whole plant is housed inside this building here. The plant's capable of turning out up to 10 gallons of it every minute, and even that's quite small compared with some acetaldehyde plants in other countries. But if this stopped operating, there would be headaches for some chemical manufacturers who use acetaldehyde to make a variety of more directly useful compounds. The reaction going on in here is the oxidation of a primary alcohol to an aldehyde. This is one of the reactions you saw in the previous TV program about organic synthesis in the lab. Quite a difference. That was a nice, quiet reaction done in simple glass apparatus. The product was simply distilled out of the flask, condensed, and then dried. This industrial oxidation is in no way a mere scaling up of what's done in the lab. There are lots of reasons for this, and some of them are economic. Imagine the expense of using vast quantities of potassium dichromate, and the problems of dealing with all the chromium salts in the effluent. And perhaps less obvious, it would be very expensive to multiply up the wasted heat that normally goes in warming up the lab or disappears down the sink in the cooling water. The alcohol being oxidized to acetaldehyde is ethanol. The oxidizing agent used is atmospheric oxygen, a favorite oxidizer of the commercial chemist as it costs nothing as a raw material. The oxidation products are acetaldehyde and water. Acetaldehyde is one of a family of 2 carbon compounds that is made directly or indirectly from the crude oil fraction known as naphtha. You've already seen that naphtha can be cracked to produce ethylene. Ethylene can be oxidized directly to acetaldehyde, but this process is not operated in the UK. The method used in this country is indirect. First, ethanol is made by the hydration of ethylene, and then ethanol is oxidized to acetaldehyde. This acetaldehyde plant is part of the BP chemicals complex at Salt End near Hull. There are a number of advantages in carrying out several related chemical operations on the same site, not least because it avoids the need to transport large amounts of hazardous chemicals by road or rail. The acetaldehyde plant is part of an integrated system here. The plant itself is quite complex, so let's start simply. The ethanol starts in the evaporator, where it is vaporized, and then mixed with air, which contains oxygen, our other reactant. The mixed gases are led to the reactor. Here they pass through a layer of catalyst, and it's here that the chemical reaction occurs to produce acetaldehyde. All of the oxygen is used up, but not all of the ethanol, because it is deliberately in excess. The products go next to the heat exchangers, where their heat generates steam for use in a later purification process. In the second set of heat exchangers, a good deal of unused ethanol is condensed. Most of the acetaldehyde, on the other hand, is still in the vapor. Its boiling temperature is only 21 degrees centigrade, and it's scrubbed out. That is, the vapors pass up a scrubbing tower, down which aqueous ethanol is flowing. The ethanol dissolves out the acetaldehyde. The vapors now go on to a second scrubbing tower, where water is used to remove all the remaining ethanol. The other gases that are left go to waste. These are mainly nitrogen and about 15% hydrogen. The hydrogen is formed in the reaction, as you'll see shortly. The liquids containing the acetaldehyde, mainly those from the first scrubber, go to a pressure still. Here, fractional distillation allows pure acetaldehyde vapor to be taken off at the top, and this is condensed and stored. From the bottom of this fractionating column, a water-ethanol mixture emerges. Some is used in the first scrubbing tower. The rest goes to another still where ethanol is recovered and then is recycled as vapor to the evaporator, where fresh ethanol feedstock is also added. The process is continuous and is maintained working for up to a year at a time. The heart of the plant is the reactor vessel where the chemical change takes place. Here's one that isn't in use and we can look inside. This is the bed of catalyst, and it's about 2.5 or 3 centimeters thick. The catalyst is silver, and at 1979 prices, the bed would cost about £15,000. But the silver is a catalyst, and so it is not used up in the chemical reaction. It needs to be regenerated about once every 2 or 3 years. But in fact, if the price of silver is increased in the meantime, this means that the trade-in value of the spent catalyst may well be more than the original cost when new. When the reactor's in operation, the catalyst bed gets very hot. The vapors reach it at about 90 degrees centigrade and leave at 500, and the whole reactor house is very warm. Let's look again at one of the reactors that's actually in operation. The exact temperature of the catalyst bed is important. If it's too hot, some of the acetaldehyde is decomposed to carbon monoxide and methane. Too cold, and not all of the oxygen is used up. Some of it gets through the bed and oxidizes acetaldehyde to unwanted acetic acid. So good control of temperature is needed. And in the reactor, it's the composition of the vapor mixture that is critical. The reason is that 2 reactions are going on in here. Not one, but 2 reactions at the same time, and both are producing acetaldehyde. The catalytic oxidation of ethanol is the major process. The second reaction is the catalytic dehydrogenation of ethanol, producing acetaldehyde and hydrogen. Remember, I mentioned that the waste gases from the process contain nitrogen and hydrogen. This is where the hydrogen comes from. The oxidation reaction gives out heat, but the dehydrogenation absorbs heat, and the balance between these two maintains the temperature of the reactor so as to avoid unwanted byproducts. The temperature is monitored down in the control room, but we can get a visual check of what's going on through one of these viewing ports. At the moment, the catalyst bed is fairly uniform in temperature, but an experienced operator can tell when cold spots are developing and oxygen is getting through. So the temperature of the catalyst bed is governed by the composition of the vapor mixture in the reactor. But how is that composition controlled? To find out about that, we'll have to look down below. Here in the evaporator, the ethanol is at about that level. And air is blown in through these pipes at the side. Now, the rate of evaporation of the ethanol is controlled by the temperature and the pressure. What we do is to fix one of these 2 variables and use the other to control the rate of evaporation. It's the pressure that's kept constant. That isn't as straightforward as it sounds, because atmospheric pressure varies from day to day, and it's the absolute pressure that must be constant regardless of the outside pressure. But with the pressure constant, then the temperature of the evaporator controls the composition of the vapor mix, and hence the temperature of the reactor up there. What we do down here is to heat the evaporator with steam, and water pipes cool it down. And the use of these 2 is very important in careful temperature control. You'll appreciate what I mean when I tell you that a 1 degree rise in temperature down here can mean a 16-degree rise in temperature up in the reactor. An upper limit is set for safety, and if the reactor temperature exceeds that limit, then the air supply is automatically cut off. So the ethanol is vaporized in the evaporator and oxidized in the reactor. What do we want of the products from the reactor output? Well, there are three valuable components. There's the product, acetaldehyde, that must be separated and purified. There's the excess ethanol to be recovered and recycled. And there is heat, put to good use in other parts of the plant. Let's see how the acetaldehyde is recovered. This is a pressure still. Now, since acetaldehyde boils at 21 degrees centigrade under normal atmospheric pressure, that's far too low for it to be condensed with cooling water at 23. So we resort to fractional distillation under increased pressure. At 18 pounds per square inch, the boiling temperature of acetaldehyde is raised to 46 degrees. From the top of this still, 50 feet up, pure acetaldehyde vapor is taken off and condensed, and the liquid acetaldehyde is piped to storage outside the building. From here, it's transported by tanker to different plants to be used as an intermediate in the synthesis of other organic compounds.
Right, Stan.
Going back to our family of two carbon compounds, some of these are used as solvents in such things as varnishes or printing inks or adhesives. Esters are particularly useful solvents, and ethyl acetate is made on a large scale mainly for solvent use. BP Chemicals is the sole UK producer, and annual production is about 40,000 tonnes. Ethyl acetate can be made from acetaldehyde, but this is not the method used at Hull. More conventional is the route from acetic acid and ethanol. Acetic acid in turn used to be made by oxidizing acetaldehyde, but now it comes from the direct oxidation of the hydrocarbon mixture naphtha. The reaction between ethanol and acetic acid is quite slow at ordinary temperatures, and even when equilibrium is reached, there's still a lot of alcohol and acid present. The achievement of equilibrium can be speeded up by heating or by using a catalyst or both. And in the laboratory, the position of equilibrium is shifted by using a large excess of one reactant, usually ethanol. Well, commercially, much the same is done, except that recovery of the product in high yield is achieved by constructing a by now familiar-looking plant like this one. Within the plant, there's a distillation system where the conditions are arranged so that pure ethyl acetate is recovered and the rest of the mixture is recycled. Esterification takes place in the reactor. The rest of the plant is for separating and purifying the ester. The reactor has a feed pipe for the ethanol and acetic acid mixture, and the strong acid catalyst is already inside. Heat is supplied through internal steam pipes, and the heat also vaporizes some of the mixture, and this is the beginning of the distillation sequence. One of the people best qualified to tell you about the distillation is the principal designer of the plant, Les Fish.
Distillation is a complicated separation process, and very often it is difficult to obtain a pure component in a straight distillation. In our reaction here, we do have a mixture of an ester, an alcohol, water and an acid, which is non-ideal. However, in this case, the non-ideal behaviour enables us to design a relatively simple and efficient process to give pure ethyl acetate. As John said, the vapour from the reaction system, which contains the manufactured ethyl acetate and water and acid and a bit of alcohol, comes along this vapour line into this distillation column. This distillation column has been designed to return the acetic acid out of the base back into the reaction kettle, and at the same time the overhead vapours from the top of the column are ethyl acetate and water with no acid in it. This acid-free vapour with the ethyl acetate and water in it, coming from the top of the column, passes to the condenser cooler, and it comes out of the bottom as a cold ester water mixture along this pipe into the decanter, where it separates into two layers. The lower aqueous layer, with a few percent of ester and alcohol in it, is pumped away along these pipes and pumped to a distillation column in the next structure to recover the ethyl alcohol, which passes back to the reaction system. The upper ester layer, containing about 5% of water, is pumped by a pump at the back, a portion of it going back to the top of the distillation column to suppress acid distilling, and at the same time to remove the water of reaction. The excess ester layer, which is our make, is pumped to that distillation column, which removes the alcohol and the water and gives us dry ethyl acetate as a bottoms product out of the column. As in the majority of organic chemical manufacture, it's not the making of the ester that uses the steam in the reaction, but it is the distillation system which we have to produce the pure components. There are two main factors in a plant like this. Firstly, the design must be safe, and secondly, it must be as economic as possible on energy usage.
So we've seen something of how acetaldehyde and ethyl acetate are made on a large scale. And you'll appreciate that industrial organic synthesis is not simply a scaling up of laboratory processes and laboratory equipment. Sometimes the chemistry is the same, though sometimes a different synthetic route is chosen. But what a contrast in the hardware. And we haven't seen a single drop of the compounds being made